X C is called a finite subcover if it consists only a finite number of elements. In other words, you can see that you can see that if there exists G alpha 1, G alpha 2, G alpha n elements of F such that the union of G alpha k runs from 1 to n is equal to whole space, then this collection, okay, which is the sub collection of F, this collection is called a finite subcover of F. Okay, so this is, and if the elements of this C are finite, or these elements of this are open sets, then it is called finite open so this is called finite subcover of open sets or open cover of X. So here is let X be a metric space and Y be a subset of X. A collection of subsets of G, the subset of X, G alpha, is said to cover Y if Y is a subset of union of G alpha. Namely, suppose here you have, suppose this is your any metric space set and this is my Y, okay, and then you have the collection of subsets of X. Suppose, so this is a collection of subsets of X, okay, so I take this. So this is my G1, this is G2, this is G3 and this one is G4. So the union of Gi is this, so Y is a subset of this one. So this family G1, G2, okay, this is the cover of Y. Okay. Now let us take some examples. Let X be a usual metric space. Okay, sorry, X is equal to R, be a usual metric space. So this is my R, set of all real numbers, and then I can have the open interval -1 to 1 open interval, then -2 to 2, -3 to 3, -4 to 4, and so on and so forth. So if we consider the family of open intervals of the form -n to n, okay, then we will see that the union of all these open sets will cover whole R. Okay, it means that this is an open cover of R. This is your cover of R, but it is open cover because the open intervals are open sets in R. So this is your open cover of R. And now you can also consider that 2n, the subfamily of this family, which is the subfamily is open intervals -2n to 2n. So this is -2 to 2, then -4 to 4, and so on and so forth. So this family, okay, you take the union of this family, that will also cover the whole R real line. It means that this subfamily of this family F also covers R. So C is a subcover of cover F. Okay, and because the elements of this set, this family are open sets, and therefore this is your open subcover and this is your open cover of R. Now take another example. Suppose we consider X is equal to open interval 0, 1 with the usual metric space. Then we can have a family F consisting the open intervals 0, 1 minus 1 over n plus 1. Okay, n is your natural number. And we can have the C, a collection C of intervals of the form 0, 1 minus 1 over 4 n plus 1. Okay, then we can see that this family is nothing but it is a subfamily of this family. And not only this, we can take another family 0, 1 minus 1 over 2 n plus 1, 1 over 3 n plus 1. You can take many subfamilies of this family. And then you can see that if you take and these are what? These are the open intervals. So open intervals are open sets. Okay. So open sets in 0, 1. Keep in mind, I would take, I recall you that suppose this is your R. Okay. Here you have 0 and you have 1. Okay. Then the open interval in the set X 0, 1. What will be then? You take the open interval with the intersection of X. Okay. So open interval, suppose I take the open interval this minus half and half. Okay. Minus half and half. Then, so this portion 0 and half, this is an open interval in X. So similarly, we will see that all these elements of F are open intervals in 0, 1. Okay, in the metric space 0, 1. So these are the open sets in the metric space 0, 1 with the usual topology. And this family is a subfamily of this family. So this is an open cover of 0, 1 and this is a subcover of this family. Take another example. Suppose I have R2, the plane. This is my plane. Okay. And suppose I consider a family as F whose elements are open spheres with center at X, where X is of the form X is equal to n, n, where mn are integers. Okay, with radius 1. So here is suppose the m is equal to 0, n is equal to 0. Then we have this ball. Okay, this open sphere with center at origin and radius is 1. Now, if m is equal to 1 and n is equal to 0, then we have this one. Okay, this is here my open sphere with radius 1 and center 1, 0. Now, if we have 1, 2, 3, so 1, 2, 2, 0. Okay, so m is equal to 2, n is equal to 0 and radius is 1, then we have this ball. Okay, similarly, we can go and other way. Suppose I have 0, 1, 1 and okay, 1 minus 1. Okay, 1 minus 1. Then I have this one with radius is 1. So this circle. In this way, if you take the union of the family of members of F, which are open spheres with center at X, where X is equal to mn, where mn are integers and radius 1, then the union of all these open spheres will cover whole R2. Okay, and therefore this family F is nothing but it is the cover of R2. But as we have proved that every open sphere, okay, is an open set. So this is your open set in R2 because we are considering R2 with the usual matrix. So this is your open sphere, open set in R2, and so F is an open cover of R2. So this is your open cover of R2. On the other hand, if suppose we consider a family C, okay, with the same center where the center x and x is equal to mn and mn are integers, but I am considering the radius is half. If I take here is the radius is 1, so if I take the radius is half, then what will happen? Then you will see that if it is 1 1, radius is half is this portion, and then from here is half, and this center is this one. So 1 0 and the radius is half. So we have this sphere. If you have 1 1, then so this is 1 1. So this is your open sphere with center at 1 1 and radius is half. And here is we have 1 0. So this is your open sphere half. But you will see that we will get like this. So here is we have gaps. So this point y is equal to half half. This point does not lie in any sphere. Similarly, all the points here they do not lie in any open sphere, and you can consider the points here and here and here and here and so on. It means that if we consider the family C of open spheres whose center at x and x is equal to mn are integers and radius is half, then this family will not cover whole R2, and therefore this family C is not a cover of R2. Okay. Now let's come to the definition of formal definition. I can say that because so far we have studied in the course of reanalysis every closed and bounded subset of R is called compact set. But here it is not a very formal definition. So we must have some kind of formal definition which is true in all the cases, because every bounded, closed and bounded subset in the metric closed and bounded subset of R are compact or are called compact, but it is not true in general. For example, it may not be true in the setting of metric spaces. So we have to give the definition of a compact space or compact metric space. We should give a formal definition of a compact metric space. So let X be a metric space. Then X is said to be compact if every open cover of X, has a finite subcover. If every open cover of X has a finite subcover. Okay. So, and if y dy is a subspace of a metric space XD, that is to say y dy is itself is a metric space, but y is a subset of X and dy is the restriction of D on Y. Okay. Then the subspace y dy of a metric space XD is called compact if this space y dy is compact as a metric in its own right. In other words, every open cover of open sets in Y has a finite subcover. Yani ke you see that every here the compact set means every open cover of X has a finite subcover. So the open sets, okay, so open sets in X. So here is the open set. When we talk about the subspace, then we consider every open cover of Y which sets open in Y has a finite subcover, then y dy is called a compact space or compact subspace. A subset y of a metric space X is called compact if it is compact as a metric subspace. So again, if you have a subset, we should make this as a subspace of y by introducing a restriction of a metric D, that is your dy, and the y, okay, has a open cover by sets open in y has a finite subcover, then y is called compact. Okay. In other words, a non-empty subset y of a metric space X D is compact if it is a compact metric space with the metric induced on it by D. Now, let us take some examples of a compact space or some examples of a. So, first you see that we have seen that we have seen that this F is an open cover of R. So, if you take the union, it will cover whole R, and this is also a cover of R. Okay, and not only this, but this C is a subcover of F. But both the families F and C are not finite. Okay, and you cannot find any finite subfamily of F or Fc which covers whole R, and therefore this F does not have a finite subcover of R, and therefore the R is not compact. So the usual metric space R is not compact. Now you can consider in this way that consider on open cover, this one which I have showed you, that is from -1 to 1. Okay, and here is these are open intervals, and if you take the union of these open intervals, it will cover the whole real line, and then naturally F is an open cover of R. And let us take a finite subfamily of this one. Finite subfamily means minus ni to ni, I runs from 1 to k. So this be a finite subcollection of this collection, and let us take n star is the maximum of n1, n2, nk up to here, all these maximum of n1, n2, nk. And then we can see that the maximum of this okay, will not be in the union of ni open intervals ni minus ni, because this is the maximum of this one. So this, of course, this is not in the union of this one. It means what? It means that this family, okay, does not cover the whole space R, and so thus no finite subcollection of F of this family cover R, and hence R is not compact. Take any finite subset Y of a metric space X is compact, because in this case every open cover of Y is finite. So you can treat every open cover has a finite subcover. So it means that you already have a finite cover, so subcover you can treat as itself. So it has a finite subcover. So every finite subset of a metric space is compact. Now, what about the set of integers with respect to the usual metric? Usual metric means mod dxy is equal to mod of x minus y. So set of integers with respect to the usual metric is not a compact metric space. Why it is not a compact space? Every integer can be written as z intersection n minus 1 over 2 comma n plus 1 over 2. So if we take the intersection of this, we will get n. N is your integer. So for every integer can be written in this form. But this is what? This is your open set in R. And if you take the intersection of open set in R with Z, then it will be an open set in Z. So it means that this is an open cover of Z. So this will cover the whole Z. But this open cover does not have any finite subcover, and therefore Z is not compact. Okay, let's take one more example. So if I take a subspace X is equal to 0 element union the elements 1 over n is your natural number. For example, we take 0 union the set consisting your 1 over 2, 1 over 3, 1 over 4 and so on. Then this set, okay, this set is your compact set. How it is compact? Let us see. If F is a given open cover of X, okay, then we will have to prove that it has a finite subcover. So then there exists an element G of F, because our family is what? Family is like this. So I take, so we have, suppose this is my 0, okay, and here you have, suppose this is your 1, so elements are 1, then you have 1 over 2, okay, so this is your 1 over 2, then 1 over 3, and then 1 over 4, and so on and so on and so on, and 1 over 100, okay, and here you see 1 over suppose 1000. So what we can do here is, suppose we have F is a family of open cover of X. So we can consider the elements, okay, we can take the G a set from this family, okay, G we can take a G element of this which consists 0. So suppose, so what will be happen? This is your 0 containing 0, okay. So this open cover, so it is like this, okay. So this is your G. So take, and then from here, up from here, so it may be 100, 1000 or something, and then these are sets, rest of the sets are finite, okay, and you include this set. So this set, and so it is a cover of, so we can take a F, so we can take any, so F is a given open cover, then there is an element G of F consisting 0 element. Then G contains all but finitely many of the points 1 over n. So for each point of X not in G, choose a member of F containing it. Then the collection consisting of all members of F along with the member G. It is a finite subcollection of F that covers X. Okay. So this is your, so this was any given, any arbitrary open cover. So this open cover has a finite subcover, and therefore this set is your compact subspace of R. Now take one more example. Suppose we have a set of real numbers with the usual metric. and Y is our subspace, okay, which is equal to open interval 0, 1, and of course this is a subspace of R, okay. Then this subspace of R is not compact. Why it is not compact? Let us take here is we have this is 0, 1. So this my open interval 0, 1. Okay. Now consider a class of open intervals of this form. That is to say 1 over 3, 0. So 1 over 3 from here 1 over 3 to 1. Then 1 over 4 to 1 over 2. Then 1 over 5 to 1 over 3. Then 1 over 6 to 1 over 4, and so on and so forth. So this from here to here, this is your open interval. Okay, let me call it, this is G1, this is G2, this is G3, this is G4. So G1, G2, G3, G4, and go up to end. What we will see? We will see that the Y, which is equal to 0, 1, is the union of Gn, where n runs from 1 to infinity, and Gn is equal to 1 over n plus 2, comma 1 over n. So the intervals of this form. So you take the union of all these intervals, okay, which are open sets in this open sets in this space, okay. So the union of this is equal to Y, and therefore this F is an open cover of Y. But this open cover of Y, okay, contains no finite subcover. Why it is so? Let us take F star consisting of finite number of intervals, which is A1, B1, A2, B2, A and Bn. Be any finite subcover of this cover. Okay, suppose F star be any finite subcover of the cover F. And if epsilon is equal to minimum of this A1, A2, An, okay, then of course the A1, A2, An, then epsilon must be strictly greater than 0. And we can take A1, B1 union, take all the union of this one, okay. So that the union of all these intervals would be a subset of epsilon 1. But 0, closed interval epsilon, and the open interval epsilon 1, they are disjoint. It means that there some elements, so because they are disjoint, so you take from 0 to epsilon, and then, okay, including the epsilon, and then the open interval from the epsilon to 1. Okay, so they are disjoint. So it means that if you take the union of this, it will not cover the whole open interval 0, 1. Okay, and therefore this subfamily, okay, a finite subcover, which we are saying that is not a cover of Y, and so Y is not compact, and therefore this set is not compact. However, we can take Y is equal to the open interval 0, 1 and closed interval 1 of the usual metric space R. Okay, then again Y is not compact, because the open cover of the form, the open cover F, which consists the open intervals 1 over m, comma 1 closed interval, okay, contains no finite subcover of this space. On the other hand, we can see that if we are considering the closed interval 0, 1, okay, then this set is compact. Okay. Now, take some other examples after this real line. So, we have an open sphere with center 0 and radius 1. Okay. The open sphere with center 0, radius 1 is not compact. Why it is not compact? We can see that the open sphere, okay, is the subset, the open sphere lies in the open sphere, the union of open spheres whose center at 0 and radius is 1 minus 1 over n. Okay, so then this family of open spheres, this family, these are the open sets. So this family is an open cover of S10. Okay, but this family of open cover of 0 has no finite subcover of this cover, and therefore S10 is not a compact set or compact space. Let us take, as I mentioned earlier, whenever we discuss any example in the metric space, you must try first the real line, okay, whether real line satisfy the conditions or not. The second is for the counter examples especially, you must try to check the discrete metric space. Okay, and you know that in the discrete metric space, every subset is closed as well as open. And if X is a discrete metric space and it is infinite, okay, then it is not compact. If it is finite, of course, because every open subset or every subset of a discrete metric space is open, okay, and if it is finite, so it has an open cover, a finite open cover, and so it has a finite open subcover, so it is compact. Okay, but in general, every finite set is compact, so it is compact. But here is if X is your infinite, okay, infinite set with respect to, and D is the discrete metric, then X is not compact, but it is closed and bounded. Keep in mind, it is closed and bounded. So what we have learned in the real life is a closed and bounded subset of the real line is called compact. But here we have the example that a set is a closed and bounded subset of a metric space, which is a discrete metric space, may not be it is not a compact set. Now you can see that we can consider a family F consisting the singleton sets of subsets of X, which is an open cover of X. Okay, because singleton sets are open sets with respect to the discrete metric. So we can cover the whole X by taking the union of the members of F. Okay, so cover of, since in the discrete metric space every subset is an open set, and so the singleton set, but there is no finite subcover of F that covers X. Further, any infinite subset of a discrete metric space is not compact. Now, we can have one very simple lemma, that is to say, let Y be a subspace of a metric space X. Y be a subspace of a metric space X. Then Y is compact if and only if every cover of Y by sets open in X contains a finite subcover of Y. So what we have mentioned, that Y is a subspace of X. So Y is a subspace of X means Y is a subspace of X means every open cover of Y by sets open in Y has a finite subcover. But here is we are saying that Y is compact if and only if every open cover of Y by sets open in X has a finite subcover of X. So it means that by using this lemma, we are not worried about whether the elements of an open cover are open with respect to the metric on X or with respect to the metric on Y, that is to say on the restriction of the metric on Y. Okay, this is very important point here is Y, again I am repeating, Y is compact. Y is compact means Y is a subspace. Keep in mind, Y is a subspace of a metric space X. So Y is compact means that every open cover of Y by sets open in Y has a finite subcover. Now this lemma says that the Y is compact if and only if every open cover of Y by sets open in X, okay, not necessarily in Y, by sets open in X contains a finite subcover of Y. So we are not, whenever we talk about the compactness of Y, we can say that whether a subset Y of a metric space X is compact if every open cover, whether is open in Y or open in X, has a finite subcover, no matter. So this is very important. So a subset, we can say that is with, after this lemma, we can say that every open cover of Y by sets either open in X or open in Y has a finite subcover, no matter whether open in X or open in Y. So both way is correct. Okay. So let us prove this one. So it's a very important result. So suppose that Y is compact and F is equal to G alpha, alpha is in lambda, is an open cover of Y. Okay, open cover of Y. When we say that Y is compact, then it means that the elements of this open cover are open in, and they were so we are considering this, the elements, the element of this sets are, they are open in X. So suppose that Y is compact, it means that every open cover of Y by sets open in Y has a finite subcover. So we will have to prove that the open every open cover of Y by sets open in X has a finite subcover. Okay, so suppose that Y is compact and F is equal to G alpha is an open cover of Y by and where G alpha are open in X. Then the collection F star, which is equal to G alpha intersection Y. So G alpha, because G alpha is open in X. Okay, so G alpha intersection Y is open in Y, and therefore F star is equal to G alpha intersection Y. This is an open cover of Y by sets this G alpha intersection Y by sets the open in Y. Now since Y is compact, so this open cover, okay, by sets open in Y has a finite subcover. So since Y is equal to F star has a finite subcover C star of Y, that is of this form. So this is the finite subcover of this cover, such that because this is a finite subcover of Y, so the union of all these elements must be equal to Y. So Y must be equal to I runs from 1 to N, G alpha K runs from 1 to N, G alpha K intersection Y. And this implies that what? This implies that, and this is a, because G and G alpha K, okay, intersection Y is a subset of G alpha K. So Y is a subset of this one. It means what? It means that C is equal to G alpha 1, G alpha 2, G alpha N. This is a finite subcover of Y. Okay. So what we have done? We have taken that this is a finite subcover of Y. It means that, and here these are the elements of what? They are the open sets in X. So every open cover by sets open in X contains a finite subcover. Okay. Now for the converse, assume that every cover of Y by sets open in X contains a finite subcover of Y. Then we claim that Y is compact. So Y is compact means, let us take F star is equal to G alpha star be an open cover of Y by sets open in Y. Okay. For each alpha in lambda, choose a set G alpha open in X such that G alpha star is equal to G alpha intersection, because this okay, we are assuming that this is your open set. Okay, this is your open set in Y. So we can choose a corresponding to this open set, we can choose a G alpha open in X such that G alpha and intersection is equal to this one. And now since see F star, this is an open cover of Y. Okay, then Y must be equal to the union of G alpha star and G alpha star, because this is equal to G alpha intersection. So this is equal. Now we can write this is equal to in this way. And then we will see that Y is a subset of union of G alpha, alpha is in lambda. And hence we can see that G alpha, okay, this family is an open cover of Y by sets G alpha open in X. By hypothesis, some finite subcollection G alpha 1, G alpha n covers Y, that is Y is a subset of this union, and thus we can see that Y is equal to union of this intersection Y. So we can take both the sides, but this you can take this is inside, but this is equal to G alpha k star. So this is alpha k star. It means that G alpha 1 star, G alpha 2 star, G alpha n star, this is a finite subcover of Y, and hence Y is compact. So this way we can say that we can restate the definition of a compact subspace. So we can say that a subset of a metric space is compact if and only if every open cover of the subset has a finite subcover. Whether the elements are open, the elements of the covers are open in the whole space or in the subspace, no matter. Okay. So this is very important result.